Okay, thank you very much, Thomas. I hope you can all hear me. Good. Okay, so it's time for a fresh look at carbonate rocks. First, for those who would like to see the speaker, let me know this. Wait, I have a problem. Okay, who would like to see the speaker? You can put the window here in the top right corner. There will be no important information in this part. So if you want to see the speaker during the talk, that's the place to put me. Okay, time for a fresh look at carbonate rocks. Why do I think it is time for a fresh look? We have more than 150 years of research in this topic. It started with Henry Clifton Sorby. He was the first investigating thin sections of carbonate rocks 165 years ago. Since then, we have thousands or tens of thousands of scientific papers. We have a fantastic methods to use thin sections. As many of you might know, I'm addicted to thin sections, but we have also a lot of powerful optical tools, like electron backscatter diffraction, Raman, and so on, and a lot of other proxies that we can use, geochemical, isotope geochemical, and so on. And we have a lot of multidisciplinary studies. So why is it time for a fresh look? It sounds as if everything is basically known by now. I think it is time because we missed an important exit. And maybe we missed the most important exit. So, and I will explain in a few slides why I think so. So, how do we investigate carbonate rocks normally? So we have a research question, or even better, a hypothesis, and then we go into the field, sample our section, make thin sections, have a look at the thin sections, and then we decide based on the questions and hypothesis and based on step 1 and 2 how to proceed and which other methods should be used. Now, this is an example from my beloved island Gotland, and the thin section is actually from exactly this section. And if we look at it in detail, those of you who are experienced in looking at thin section, it's full of information. Here, for example, is a trilobite. So we know we are in a Paleozoic rock for sure. We can have a look in more detail. It's full of reef-building organisms, plenty of tabulate corals and of stromatoporoids. So this is reef debris. So probably the reef wasn't far away. If we are even more experienced, we can see here siphonal green alga. It's not so easy to recognize, but they live in the shallow subtidal environment. So thin sections are full of information about the depositional environment, but that's not all. We have also a lot of information on diagenesis, so the processes that turn the sediment into a rock and alter the rock. And there are figures like this, so we can decide or try to figure out in which of these diagenetic zones the sediment has turned into a rock and in which it has been altered. So we have sedimentological and a lot of diagenetic information in the thin section. The most common cement in coarse-grained carbonate rocks is this typical granular blocky calcite. This is an example from the Bahamas, from the Kleino core. So we have different components and we have granular calcite. So those of you who work with thin section, they will know it very well. Here's another example from the Pliocene of Rhode Island, an oolitic grainstone with granular calcite cements, and a final one, again from Gotland, here with a shell, and we have granular calcite in filling the shell and also in the between the components, so intra and intergranular blocky calcite cements. And it is known since the seminal paper of Folk in the 70s, where these cements form. Very important is the magnesium-calcium ratio. So this is shown in this diagram. And these blocky granular cements, they form from fluids with a low magnesium-calcium ratio. This is shown here in this red box are the cements, and in this bluish box here are the water masses from which these cements precipitate. And fluids with a low magnesium calcium ratio are basically either freshwater, so rivers, lake, groundwater, or pore water, so subsurface water. These are the two water bodies that have low magnesium-calcium ratio, in which these blocky calcite spar can precipitate. Okay. The marine cements in either marine water or from hypersaline brines, they look completely different. They are not the topic of my talk today, but they are easily recognizable. They have elongated crystals, fibers, needles, high magnesium calcite, or aragonite. So this is more what I'm talking about. So these low magnesium calcite, blocky, granular cements. And groundwater or freshwater is rather the exception. Of course, it occurs, sure, but a normal sediment, the normal fate of a sediment is downward. So in order to get it, a loose sediment exposed to fresh water, you need either a strong sea level drop or tectonic uplift. So the normal fate is downward. What is also typical for most limestones is that they, especially shallow water carbonates, that they lack strong indications of mechanical compaction. This is a rudstone, so a shell layer, basically crinoids, trilobites, brachiopods, and so on. And if you look at the amount of diagenetic cement in this thin section, it is way above 50%. I would say 65, maybe even 70% of sparite, of diagenetic calcite. So this shell layer was cemented prior to significant mechanical compaction. This is something that happens very early, this cementation. We see it based on the lack of the compaction phenomena. So now, why is it a problem? Why should we have a fresh look at carbonate rocks? And I think because we missed half of the story. And if we look at the section here, where do you take the sample for your thin section? Of course, from these hard layers. This is a nice layer here, or this very coarse reef debris here on top. This is the samples that you take. Or here, another example, more fine-grained. Where would you get a sample for a thin section? For example, here in this layer, or in this layer, or the others. For sure, not in the layers in between. These marly, brittle, easily weathered sediments, it's almost impossible, or in this case, I would say it is impossible to make a thin section out of it. So, and there's an important story hidden in these layers in between. And they are widely distributed. So we called it bipartite lithologies. It is very common in carbonate rocks that we have these hard and soft layers. They can look very different, as you see it here in these two plates. They can be nodular, they can be well-bedded, thick-bedded, thin-bedded, limestone-dominated, or marl-dominated. So the variability is enormous. But what they all have in common, they have hard limestones and softer interlayers here. And the goal, well, here, this is an example from a core. So if you want to make a thin section that shows also the marl, the best possibility would be core samples where the marls are still not weathered. So this is a nice example of a nodular limestone marl alternation from a drill core. So what is the approach here in my talk today? We have a very nice teaching collection here in Erlangen, a very nice and very big teaching collection. And I went through the whole collection searching for thin sections where the transition from hard to soft lithologies are preserved. And I found 12. I found 12 samples where the transition from limestone to the softer interlayer marl, shale, as you would call it, is accidentally preserved. So not on purpose, only 12. This is a very low number because normally it's not, well, the material just falls off. So, okay. And I will show you the 12 examples briefly. I will more or less jump through the 12 samples. You see the number down here in the corner. So this is the first one. And I will briefly guide you through the 12. This is a crinoidal brachiopod limestone. You see it has big cements, no compaction. These are syntaxial cements, so syntaxial overgrowth. There seem to be some remnants of marine cements, but no no compaction. And if we go now towards the edge of this limestone layer, it looks completely different. It's the same sample, the same thin section. This is how it looks like at the edge. We have the cements, they disappear. Here are the last ones. Here on top is the edge of the limestone layer. We still have our crinoids, but they show pressure dissolution features, fitted fabric. The sparite disappears. Clay gets more enriched. So there was no compaction phenomena in the center of the bed, but at the edge. This is another one. This is a small movie. I'm not sure how well it is visible in Zoom, these moving pictures, but I will show you photographs of this sample in a minute. So we have our, this is the outer part of the thin section. This is the marly part, and then downwards is the limestone bed, the soft and solid bed, and now we will move downwards. So you see here we have the shells. They are aligned, partly broken. Then we reach the center of the limestone, a lot of sparite, no compaction phenomena, nice geopetal structures. Here we are nice, probably fecal pellets or piloidal cements, loosely packed, micrite in between, or probably microspar in between. And then we reach the other side of the bed. Again, sparite disappearing. The components are more common, aligned, broken. So I will show you a picture now from the top marl, then from the central part of the layer, and then the marl below. So this is a photograph. The quality is higher. What do we see? The components are broken. This is a trilobite. We have fitted fabric, so pressure dissolution contacts between the shells. Here it is super nicely visible. So this the contact here, this is pressure dissolution. The components are broken. This is how the same thin section looks in the central part. There is no indication for compaction. We have, again, a nice trilobite. Here's a very nice bivalve shell. Here is a brachiopode, microspar in between. I'm not going into microspar here. I have it done several times. And how does the marl below look like? Basically, like the one above, we have a nice trilobite fragment here. It looks a bit almost like a seahorse. Pressure dissolution features. Some of the components are broken. The brachiopode shell, for example, here is broken, pressure dissolution, and so on. The next one, this is a very nice one. It's a carbonate nodule. A carbonate nodule surrounded by marl that has an orthoconic cephalopode in it. Cephalopods are made originally of aragonite. And the boundary between this nodule and the surrounding marl is here where the yellow line is. Yes, so here, the marl, there is no marl preserved, but I would like to highlight one area here. This is here where the cephalopod shell approaches the marl. So here would be the marl. And if we look at it in more detail, we see the shell is preserved, well, not the original aragonite of the shell, but it's preserved as granular calcite. But towards the marl, it's dissolved. It disappears. What we would see from the outside is just the sedimentary filling. So looking from the outside to this nodule, it would indicate a Steinkern. So it's only the lithified filling, but inside the nodule, the shell is preserved. Example number 4, again, a section here, and we will have a look at this particular limestone layer here, because it's very nice. It's a shell bed, mostly composed of bivalve shells, also with nice geopetal structures. How does it look like in the thin section? This is from exactly this layer. We have wonderful bivalve shells, also others, some gastropods. Here's a gastropod. There are also some brachiopods and ostracods. So the boundary between the limestone layer and the marl is here. And I will highlight 2 areas. First, this one. So how does the limestone layer look like? We have our originally aragonitic shells recrystallized. This one here has nice bioerosion structures, probably fungi. I'm not sure. I'm not an expert there. And this is a blow up now from the marl layer. And we see a similar thing. It's just the shell is gone. So here was a bivalve shell. It's completely dissolved. we have this coarse material here on top, like we have it here. So in the marl, the shells are dissolved. Example number 5, from Ukraine, from Podolia, it's nodular limestones surrounded by marl. This is how a hand specimen look like. In this case, the marl, the brownish color of the marl is it's slightly dolomitized, so selectively dolomitized. How does it look like in thin section? This is again a thin section. Whoops, here is the boundary between limestone and marl. And if we look into the limestone nodule here from this area, we see similar thing as in the other one. We have a nice gastropod shell. The aragonitic shell is recrystallized. Here are 2 fragments of probably broken bivalve shells. I'm not sure, just for sure aragonitic, but gone. How does it look like in the in this case, slightly dolomitized matrix? The reddish color is due to the staining, so alizarin red S staining. We have only calcitic shells. They are sometimes broken, but the aragonitic shells are missing, and they are aligned. Example number 6. This is Hyolitina. It's an enigmatic fossil, probably mollusk type of fossil, aragonitic. So this is Hyolitina. This is not one specimen, but probably several. They have a shape like an ice cone. And what we see here is the stacking of this ice cone. It's called telescoping. The boundary limestone marl is basically here. And you see here, it's nicely preserved, recrystallized as it should be, our ostracodes. And when we go to the surroundings, the edge of the limestone layer, here is one. It's hardly visible. It's still there, but it doesn't look so nice. Here is probably another one, might be with a remnant of the recrystallized aragonitic shell. And if we approach the marl, there is nothing left. So here we are not even sure if these were really Hyolitina or not. And this is just, if you look at the scale here, 1 millimeter, this is something, this transition from these aragonite recrystallized shells to the area where it's completely absent, this is something that takes place in the examples that I will show in a millimeter or 2 millimeters. This is one of the nicest examples I found in the teaching collection. It's again from Ukraine, it's from the Devonian. It's a shell layer with bivalve shells, recrystallized, and these roundish structures are tentaculites. Tentaculites are also cone-shaped organisms. The difference between them and these mollusk shells in this sample is the tentaculites, they were all calcitic, so diagenetically more stable. I will again highlight 2 areas here in this thin section. The boundary between the hard limestone and the soft marl is here. So this is the same thin section. And if you look at the bivalve shells, this is how they look like in the limestone, recrystallized shells. And if we zoom into the marl layer, we see the same thing. Here was a shell. It's dissolved. The tiny little components are strongly aligned. So they show this bedding parallel alignment, which is far less obvious here in the lower part. Number 7. Oh, sorry, this is the same thing. It's a small movie. We will just move now from the central part of the layer towards the marl and look what happened to the aragonitic fossils, and look also, focus also on the small components here and the alignment, how they are oriented or orientated in this sample. So we will again move towards the marl. So we are still in the limestone. We have our calcite spar, and now we are approaching the edge of this limestone layer. The components are strongly aligned. Tentaculites are still present, but no aragonitic fossils. Number 8. This is from the Muschelkalk in Germany, Garnberg quarry, upper Muschelkalk. Muschel in German means bivalve shell or bivalve. And in the Muschelkalk, most of the bivalves in the Muschelkalk are aragonitic, and the limestone marl boundary, if you want, is basically here. And you see here in the limestone part, the bivalve shells are nicely preserved, recrystallized, and then again within, let's say, 2 millimeters, they they fade away. This is here. Look at this one. This is we can still see one valve of the bile valve, and it's articulated. So here is the other valve, and here it fades away. It disappears. It dissolves. It's gone. And here, if you are really in the central part of the mal, it's only calcitic fossils left. Other quarry, but also Muschelkalk, also other Muschelkalk. Here is more or less the boundary between the lithified limestone and the soft marl, and I will focus here. What do we see? Plenty of gastropods. Here, these roundish structures are all gastropod shells. Here is a wonderful echinoderm fragment with a syntaxial sparite around it. And if we look at the marl, it looks different. We have broken and only calcitic shells, broken pressure dissolution, quartz grains, which are also here in the lower part, are they are more common in the marl area. And this is, I think, this is the same sample, so it's just another part of the same thin section. Here in below we have our limestone, above is the marl, the boundary is more or less here, and we see the components broken, enriched. Even these brownish components, they also occur here, but they are more common. These are phosphatic components, probably fish remains. If we cross the polarizers, we see that for example, the quartz grains, they are enriched here. All the non-aragonitic components are enriched, so more calcitic shells, more aligned, and partly broken. So we are approaching the end now. Number 10, another Muschelkalk example. Again, the boundary here, the same picture. So this is really, for me, it was really fascinating that all these 12 examples that showed the transition showed basically the same thing. So here, well cemented, not compacted limestone layer, and enrichment, alignment, breakage, and pressure dissolution in the marl. This is the only example that was published, and this is by Teresa Noel from Permian of South China, but it's actually a very nice example. It's full of aragonitic components. In this case, these are not bivalve shells. These are aragonitic phyllowid algae, or originally aragonitic phyllowid algae, and dasycladocyanins or dasycladolians. And the boundary is here. And if you focus here on this is a fragment of a phyllowid alga. And if we zoom in, we see it has nice sharp boundaries here in the limestone part of the sample, and it fades away, it dissolves towards the marl. We can color the components. So these are all the components that were originally aragonitic. If you look at the structure of this thin section, look at this. This is biotubation. So, and here, not so obvious, but here it's also. So this is a heavily biotubated lagoonal mud full of aragonitic fossils. In the marl part here, there is not a single fragment of an aragonitic fossil. They have been dissolved completely. If we color the calcitic parts, the same thin section, just go back. So the same thin section, this is now the calcitic parts. What do we see? We see basically the same groups, the same organisms in the marl area than we see in the limestone area, just more abundant, more enriched. So number 12, the last example, this is from the Ordovician of Anticosti Island in Canada. This is also a super nice example. The boundary between the limestone and the softer interlayers. I will highlight again this area here. So we see the boundary in this case is super sharp. We see cemented limestone with nice components, and towards the marl, they are broken, they are aligned, and we see pressure dissolution structures here and there. So what is the summary of the observations of these 12 samples? In the limestone, so in the cemented part, there is almost no compaction. So in many thin section, you don't see any compaction, sometimes a little, but normally there's no compaction. We have calcitic and aragonitic fossils preserved, also, and of course not in aragonite anymore, but recrystallized. So the aragonitic fossils are replaced by granular calcite. And if we have cement, So we see often granular cements. But very often it's fine-grained, and it's usually microspar. What do we see in the interlayers? We see strong phenomena of compaction. We see bioclasts are aligned due to the volume reduction of the sediment. They are often broken. We see fitted fabric, so a pressure dissolution feature. Aragonitic fossils are completely missing, except for imprints or steinkerns. That's the only possibility. And in all the non-aragonitic components, biogenic as well as non-biogenic components are enriched. So what are the information that we can get out of it? If we have no compaction, it means that the cementation of the limestone happened before compaction, which means in the lowermost part of the sediment column, also in the very shallow part, so close below this, the seafloor. The aragonitic fossils are replaced by granular calcite. This means the rock has been cemented before in order to fix the outline of these components, and they are dissolved after this very early compaction. And the mold is later filled with cement, with granular calcite. So, and what does the granular calcite, the cement, mean? The cementation was in a fluid with a low magnesium-calcium ratio. This is very important. So the fluid was not marine. It was at least not normal marine. It had a very low magnesium-calcium ratio. What does the compaction, alignment, and fitted fabric in the interlayers mean? It means these rocks are not cemented, those are not early cemented, and the compaction is due to the sedimentary overload. So this is a late diagenetic structure. This happens far later than the cementation. The aragonitic fossils are gone, but in order to dissolve aragonite, we don't need high pressure or temperature. This is also something that happens very early. We need, let's say, aggressive water to dissolve aragonitic fossils. And all the non-aragonitic fossils are enriched, and this is a passive enrichment. The simple reason is if you do not cement but compact the sediment and remove the aragonitic fossils, you passively enrich all the non-aragonitic parts. So let's have a look into the sediment column. These are biogeochemical pore water zones in the sediment. This is known for long. We have very different zones characterized by specific consortia of bacteria. So in the shallowest part, we have the bacteria that use the free oxygen for the decomposition of the organic matter. And then we have the nitrate reducing bacteria, manganese reduction, iron reduction. And in the marine environment, very important, the sulfate reduction. And then we have the methanogenesis, and in between, a very important zone that is called the sulfate methane transition zone, or the zone of anaerobic oxidation of methane. In shallow water, we are talking about 1, 2, 3 meters of sediment depth. So this is something that is very close below the seafloor, just a few meters, sometimes even less than a meter. So, and the important thing for me is that every sediment that is deposited here on the seafloor eventually penetrates through all these different layers. And the pore water chemistry in these layers is very different. So they experience very different, geochemical pore water zones, if you want. What is a bit surprising is, if this is really the zone where we have the aragonite dissolution and the calcite precipitation, we don't know yet precisely where this happens. There are different ideas around. This is, for example, this is from the paper that we have just published. This is the idea that Paul and Leslie favor dissolution in the taphonomically active zone, with a very strong loss of most of the dissolved aragonite, and part of the aragonite is precipitated in the sulfate reduction zone, probably in the upper part. This is the idea that Teresa and myself favor, precipitation in these AOM and dissolution above and below. But honestly, this is all only this. It has never been observed in flagranti. This is just based on interpretation of fossil carbonates. What are the diagenetic stages then? We have a very early selective dissolution of aragonite in specific layers called marls or shales, or how you want to call it. And this dissolved aragonite is cementing the limestones completely or partly. That can be debated. And this is something that happens probably in the very few meters, few tens of meters maximum. I will come to this point later. So very early. And why is it low magnesium calcite? If you go back here in the very shallow water, 1-2 meters below the sediment, we would expect marine-derived pore water. And yes, it is marine-derived, and marine water has a high magnesium-calcium ratio, as we see it here. But the moment we dissolve aragonite, we shift the pore water chemistry. We shift it towards low magnesium-calcium ratio because aragonite has almost no magnesium inside. That's why the pore water chemistry shifts, and the cement that precipitate from this pore fluid, they look like freshwater cements, but are actually not. This was already known by folk. It was nicely shown by Leslie Melim when she investigated the drill cores from the Bahamas. This is one of her samples here. Super nice cement that have never been exposed or never seen a single drop of fresh water. So, and then when this is done, when the aragonite fossils are dissolved, the limestones are cemented, diagenesis of course continues. And with increasing or continuing sedimentation, we get more and more pressure. The sediments, they go downwards. The interlayers, which are not cemented, they experience more and more pressure. The components, they break, they get aligned by the increasing pressures. And finally, we see pressure dissolution structure, so fitted fabric stylolites. This can continue. Also, it starts in, I don't know where exactly, but in a few decameters to tens of meters, the compaction gets really important and can continue down to several kilometers. So in our opinion, most carbonate sediments that contain aragonite and organic material are strongly altered in the zone of early marine burial diagenesis. But the question is, why is this diagenetic zone so poorly known? If it's everywhere, and all the samples that I found here in the collection showed it, why is it so poorly known? Some of you might have listened to the talk of Christian Merz 2 months ago here in this seminar, it is sedimentology lunch seminar. This was a fantastic talk. The title was Reduced, Dissolved, Precipitated, the Multiple Effects of Early Diagenesis on Sediments and Sedimentary Rocks. I really recommend it's online. You can redigest it if you want. This was a fantastic talk. There's nothing to add except for aragonite. We know quite a lot about these early diagenetic zones, but only from settings without aragonite. We know it, as you can imagine here from this slide. The information we have on this very early diagenetic environment is from non-aragonite sittings, which means either deep water or clastic, or sometimes aragonite-free high latitude sediments. And this is exactly the thing. The moment we add aragonite to the system, that gets dissolved, redistributed, and reprecipitated, we form limestone layers. And when we have limestone layers in this shallow subsurface, we have a methodological problem. So if we use box cores, for example, so either they don't go deep enough to reach a lithified layers, or if they do, they would never penetrate it because the layer would be too hard. And even worse, if we have gravity cores like these ones, they are not able to penetrate a hard limestone layer, so they would just bend and come back on board as banana, or so-called bananas, because they are destroyed basically. So what about a proper diamond drill core? Yes, that's a possibility, but if there is a sediment, if there are sediment layers in 1, 2, 3 meters depth below the sediment surface, what would we expect? A proper diamond drill would at best get bits and pieces of the limestones, but not a proper core. And if this is described in a very nice paper by Pearson and Thomas some years ago, it could happen that a drill core gets, the proper diamond core gets a core, but only the limestones. And this is called biscuiting, or more precise, core disking. So the marls, they are too soft, they are just squeezed out, and all we see is just the early lithified layers. So it's possible, but we hardly know anything. And we have an additional problem, and this is a geological issue. So what if this is a process, if it's what I have explained now here in the past 20 minutes or half an hour, if this is really something that happens basically whenever we have aragonite and organic matter, where would we expect it to be? Here in the let's say in the lagoon, in the muddy lagoon, we would expect the lithification in 1 to 3 meter depth, or even shallower. And if we go in deeper environment, these biogeochemical zones, they go deeper into the sediment due to different organic matter and sedimentation rate, probably. So if we are here on the slope, we would have to drill 10, 20, 30 meter to get information about this zone. So yeah, well, why not do it? The problem is we are living in the wrong time to do it. This is pre-Pleistocene. What happened in the Pleistocene? All our shallow water carbonates were exposed to freshwater. They karstified. They show diagenetic freshwater overprint. So the only area where the zone could be observed even today is we have to go into areas which have never been exposed to freshwater diagenesis during the last glacial or the Pleistocene sea level drops. And this is exactly the problem. So we cannot see it here. We might see it here, but as I said, in somewhat deeper settings, not in 1 or 2 meters. So that's the reason why I think it is time for a fresh look at carbonate rocks. We know that carbonate sediments and rocks, they can be diagenetically altered in many different environments and by different processes, and sometimes by many different processes. But it's a bit surprising to me that the zone where probably the strongest changes in the sediment take place is at the same time the zone about we know the least, at least in my opinion. So that's it. I would like to say thank you for listening. Special thanks to Hildegard, Teresa, Paul, and Uwe for their valuable contributions and discussions, and all the other colleagues discussing this with me, and to Birgit for making the thin sections, and a little bit of self-promotion at the end of this talk. If you have appetite now for thin sections, you are welcome to join the Flügel courses here in Erlangen, which take place every year. But I have to warn you, the waiting list is long, so you usually have to wait a year or 2 or sometimes 3 years even for a place. So thank you very much. I'm looking forward to the discussion now.